Hi, welcome to Chem 6161. Today we will do the Felkin exercise. Okay, basically, these are the questions. We have this ketone with this chiral center in the alpha position, and we add phenyl magnesium bromide. How we do it? First, we need to draw this molecule, putting our eye here, and what we get is with the phenyl in this side, here a hydrogen and here the methyl. Next step, we put the bigger substituent. All substituents are carbon chains. That means that we have to use the Felkin model. Put the big substituent perpendicular to the carbonyl group. We have two options. Okay, and then we analyze the trajectory of the nucleophile. That will be a phenyl negative, phenyl anion. Okay, the nucleophile following the Burger-Zunitz trajectory. In this case, the nucleophile will crash with the methyl. In this case, the nucleophile will crash with a hydrogen. Obviously, this will be more stable. That means that the final product will be okay. That means if I draw it in this way, this is a methyl, sorry, but this doesn't change anything. Okay, if we draw it in this way, we have methyl, OH in front, phenyl behind, and we will have this color. Okay, this is the answer for the one. The model that we use it is the Felkin model because basically we only have carbon chains in all the substituents in the alpha position. Second one, exactly the same. This is also Felkin model because all are carbon chains around the alpha position. And we do exactly the same. We draw it. Okay, if I draw it like this, ethyl here, methyl here, hydrogen here. I have two options. I have to put the bigger substituent, in this case the ethyl, perpendicular to the carbonyl. If I put the ethyl here, okay, I have the methyl up and the hydrogen down. If I do the opposite, I put the ethyl in this side, I have the methyl down and the hydrogen up. And again I analyze the addition of the nucleophile. In this case, is crashing a methyl. In this case, is crashing with an hydrogen. Obviously this will be easier than not this. That means I will have this final compound. Nucleophile, the phenyl here, and then I will have ethyl, methyl, and hydrogen. Okay? If I draw it, what I will get is phenyl, OH in front. In this case, the nucleophile is a methyl inside, and here I will have the ethyl and the methyl. Okay, this will be the final compound. Okay, remember, in these two cases, the only that I did has been to decide that I will use the Felkin model because basically all are carbons in the alpha carbon. That means that I put the bigger substituent perpendicular to the carbon group, and then I analyze the nucleophilic trajectory following the Burgitz-Donitz trajectory of both conformations, and I choose the conformation that presents less sterical hindrance. Okay? Good. Then we go for the third one. Okay, I will copy here. We have this. We have zinc and methyl magnesium bromide. Okay, here what we have in the alpha carbon, we don't have all carbon, we have an electronegative atom, in this case a methoxide. Because a methoxide, the metal is small, what I will consider is that I can form a chelate. Also, this is reaffirmed, this is because I am using zinc plus 2. Okay? This can form a chelate between the two oxygens, and remember, when we do this, what I have to do is first draw a molecule with the two heteroatoms in the same direction, okay? If I put this up, means that the hydrogen will be here, and the metal will be here. Okay? Then I do the chelation with the zinc. This is fixed, and now I analyze the trajectory of the nucleophile. Will attack here or from behind. If the nucleophile attack from in front of the slide, he's facing a hydrogen. If the nucleophile is attacking from behind the slide, he's facing a metal. Obviously, hydrogen presents less steric hindrance, that means that the nucleophile will attack from in front. I will get metal, that is a nucleophile, OH behind, and here I will get it. Okay? The attack will take place in front because in front he is only facing a hydrogen. Last one. I have this compound, I add methyl. Okay? In this case, I consider that the dimethyl amino is enough bulky in order that don't allow a coordination, a chelation of the metal. Okay? If you explain me that in your opinion this is not enough, that means that you can form a chelation, will be okay both answer, but you have to justify which you are using. If you are using the chelation or you are using the polar model. In this case, I will use the polar model. How is the polar model? I draw a molecule. Okay. Okay. I watch the molecule from here. Next step, I put the electronegative atom perpendicular to the carbon group. I have two options. This is one, this is the other. The only difference is that I change the site of the dimethylamino, okay? And then analyze both trajectories of the nucleophile. The nucleophile always, remember, opposite to the big group or the group in perpendicular and following a Burgitz-Donitz trajectory. In this case, the nucleophile is crashing a phenyl. In this case, the nucleophile is crashing a hydrogen. That means this will present less steric hindrance. This will be the right trajectory. This is giving this product. Okay. And if I draw it in the right way, okay, what I will get is phenyl, OH in front, if I am not wrong, phenyl, OH in front, the nucleophile in this case, that is a methyl inside, and then this. Okay? And this is all. This is the 3 different mechanisms for the addition of a nucleophile to a carbonyl compound depending how is the chiral center in alpha. Okay, Felkin and chelation and polars. In the case of the chelation and polar, you always can decide which will take place. You have to explain me why you choose one or the other, and if the explanation is okay, the answer will be okay. Right? And that's all for the Felkin. Thank you very much for your attention, and see you in the next lecture.